So we at last begin the chapter on real numbers. In this foundational chapter, we shall study the basic properties of real numbers. Instead of constructing the real numbers from set theory, what we shall do is we shall list a set of axioms that completely characterize the real numbers. Recall that one of the aims is you are given a straight line and you want to measure every single quantity on this straight line. Now, several quantities you can already measure. How do you do this measurement? Well, you fix a point as the origin and fix a unit distance. That way, you will get 2, 3, so on. By just repeating this unit distance, you will be able to get all the natural numbers on this line. Similarly, you can get all the negative numbers on this line. Now you can get the rationals by marking off half, 1 by 4, so on. So you can lay out all the rational numbers on the real line. As we saw, this does not exhaust all the points on the line. The reason being that is the square root of 2 has no corresponding number which is laid out. When you lay out the rationals, there is a hole where root 2 is supposed to be. Root 2 is somewhere here. There is a glaring hole left by the rational numbers. But that hole corresponds to a point on the real line. We don't want that. In fact, we will see towards the end of this week that there are more holes than rational points. Now, one reason we have chosen not to construct the real numbers but rather list axioms that characterize the real numbers completely is because the construction of the real numbers is really long. In fact, there are several textbooks that are dedicated solely to constructing the real numbers, and the construction is not really very transparent. It requires a lot of work. So we shall quickly dispense off with these preliminaries and move on to the meat of the course. So there are several properties that are satisfied by the real numbers. We will first deal with the algebraic operations, which is going to be captured by the field axioms. The field axioms. Okay. So an operation on a set, is a function f from S cross S to itself. Okay. Now there are several operations you are already familiar with in a disguised notation. Addition is an operation, multiplication is an operation, subtraction is an operation. These are all operations defined on various sets. You can define addition and multiplication on the natural numbers and integers. Subtraction you can't really define on the natural numbers because 2 minus 3 is minus 1. The map should be to the set. It should not go outside the set. So subtraction is defined on Z. Addition and multiplication are also defined on Q. Subtraction is also defined on Q. Then division is not really defined on any of these sets because you cannot divide by 0. Okay. So a field is supposed to be a set. A field is a set with two operations called addition and multiplication. Which satisfy all the familiar algebraic properties. What do I mean by satisfies all the familiar algebraic properties? Well, the only way to make this precise is to actually list out properly what a field is. A field is a triple. First you have the set F, then you have an addition from F cross F to F, Then you have a multiplication from f cross f to f that satisfies, and I'm going to list a long set of properties, so please bear with me. 1. Commutativity. First property, that is a plus b is b plus a and ab is ba for all ab in f. This is the first property. Second is associativity. A plus b plus c is a plus b plus c, and similarly ABC is ABC. Note that for the multiplication I am dropping the symbol, times symbol. I am dropping it just as usual we do when we deal with multiplication in the real world. Nobody bothers writing the symbol for multiplication. It's understood. So this is true for all ABC in F. The third property is distributivity. So far, the properties that we have written are all got to do with either with addition or multiplication. This is the first property that involves both. For all ABC in F, A times B plus C is AB plus AC. 4. Existence of additive identity. Okay, what does existence of additive identity say? There is an element in F which we denote by 0, so that you get a visual indication of what it is, which we denote by 0. Note, this is not the same as the 0 that you are familiar with from natural numbers, integers, rational, so on. This is an abstract set which have elements that could look entirely different. This particular element we are denoting it as 0 for our psychological comfort and for the reason that it should visually reveal something about it. What it reveals is, for all A in F, A plus 0 is 0 is equal to, A plus 0 is A is equal to 0 plus A. Fifth, as you can guess, existence of multiplicative identity. Just like there is a additive identity, there is a multiplicative identity also. This says that there exists an element in F denoted 1 this time, again for the same psychological comfort, denoted 1 such that there is no reason to write 1 in F, denoted 1 such that A into 1 equals 1 into A equals A. Note, I have used the symbol dot for multiplication just for to be familiar with usual substitutions for the times symbol. Often we write dot for times. 6. Existence of additive inverse. Additive inverse. Well, for all A in F, we can find an element which again for psychological reasons we denote as minus A. This looks more like underscore A. This is not C programming, so I will write it as minus A such that A plus minus A is equal to 0. Note very carefully, I have not written A minus A is 0 because we don't have a minus operation on this set. We have only an addition and a multiplication. So that's why I'm writing A plus minus A equal to 0. Okay. which is also equal to minus A plus A. Again, this follows from commutativity, but I am just mentioning it. Seventh, existence of multiplicative inverse. Multiplicative inverse. Okay, this just says there is an element for all A in F. We can find an element. This element we usually denote by 1 by A or A inverse, such that A inverse is equal to A inverse A equal to 1. Now first, let me correct a mistake. I hope you notice this mistake. This is not true for all elements in the field. This is true only for those elements that are non-zero. For all non-zero elements, this is true. So, let me also make another correction. There exists an element in F denoted 1 such that A dot 1 equal to 1 dot A equal to A. Let me add that we require 1 to be not equal to 0. Okay. Now, the final, this actually concludes it. There's no final thing. There are only 7 axioms. I got ahead of myself thinking there are more properties to characterize. So, let's see some examples of fields. Let me just, easy way to remember is model it on Q. So, the example is Q. All the properties that are that a field has is modeled on Q. So Q is the prototype field. There are several others which are even finite, which I will not talk about now. You will see that in an algebra course. There is nothing in these axioms that rule out a field from being finite. Okay. Now one more thing I'd like to emphasize. I said that a field is a triple. That means there is a set and 2 operations, plus and multiplication. However, if you carefully observe, I have written A plus B, whereas more properly I should be writing plus of AB. Writing A plus B is known as infix notation, which is what is common in mathematics. So I have written it as A plus B. In the background, you must visualize addition as an operation that involves taking 2 elements of the set and combining it in some way. An operation is nothing but a formula for combining 2 elements. Okay. Now, we will prove some basic properties that you are familiar with from arithmetic using the field axioms. Every single property that you have studied about rational numbers, including things like binomial theorem, all the algebraic identities that you have studied are a consequence of these axioms. But I will not spend a lot of time proving everything, simply because none of the proofs are really difficult. And second, that's not the point of this course. You will anyway learn some of these proofs in a course on algebra when you introduce rings and fields. But let me just prove 1 or 2 basic facts. So proposition, both the additive and multiplicative identities in a field F are unique. The same is true of inverses. Note, when I stated these axioms, I just said there is an element denoted 1. I did not say there is exactly one element like that. Of course, you can postulate that there is exactly one element. There is nothing wrong with that, except it turns out that you don't need to, and it is a consequence of the other axioms. Okay, so for the first time, we have to show that something is unique. One tip here is that when you want to show that there is exactly one element in a set that satisfies a certain property, the way to go about it is assume there is another element 0 prime that can act as additive identity. Okay. Now what we will do is we will show that 0 has to be 0 prime. That means we will take another element 0 prime and show that it's actually 0. That's one way to show that a particular element with a certain properties is unique. So what we will do is, we already know that the characteristic property of additive identity is that 0 prime will be 0 prime plus 0. Okay. This follows from the property that 0 is an additive identity. Okay. But 0 prime is also an additive identity. So 0 plus 0 prime must be 0. The net upshot is the fact that 0 prime is equal to 0. Now the exact same argument works for multiplicative identities. Same, ditto. I leave also the proof of uniqueness of inverses as an exercise. Okay. Henceforth, we will also use the notation a minus b for a plus minus b. Okay. Let me just prove one more thing regarding fields proposition. In a field, multiplication by 0 gives 0. Well, I'm proving a into 0 is 0. This might seem comical, but I'm going to use only the algebraic properties of the field to do it. So proof, let a be an element of f. We want to show that a dot 0 is 0. Again, note that for multiplication I'm using dot notation. A dot 0 plus a dot 0 is actually a dot 0 plus 0. This is by distributivity. Okay. I want to show that a dot 0 is 0. So the aim is to show that a dot 0 acts as an additive identity. That's the idea here. So a dot 0 plus a dot 0 is a dot 0 plus 0, which is in fact a dot 0. Okay. Now I can just cancel a dot 0 from both sides. Cancelling, and I'm going to leave it to you to justify why this cancellation is allowed in a field. Okay. Then we have a dot 0 equal to 0. Fine. So I leave it as an exercise for you to formulate cancellation laws for both addition as well as multiplication in a field. Okay. Note that when you're formulating the cancellation law for multiplication, ensure that you take into account the special nature of 0. You cannot conclude from a dot 0 equal to b dot 0 that a is equal to b. That's nonsense. Okay. Now, in a field so far we can add 2 elements, but we can add n elements also. Suppose f is a field and you have n elements a1 to an coming from the field. I can just define a1 plus a2 plus dot 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 an and a1 a2 dot 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 an. Now a somewhat boring issue occurs. What is the meaning of this a1 plus a2 plus dot 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 an? You could assign several meanings to it. You could say it's a1 plus a2 plus a3 plus a4 plus dot 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 an. Okay. Technically, this is not well defined. Remember that addition is defined only for 2 elements. So what I have to essentially do to make this precise is that I have to ensure that there are parentheses at appropriate places. I can do A1 plus A2, then I can do plus A3. This will give me one element. Then I can do plus A4. This will give me another element. Then I can do plus A5 and so on and so on. And I have to put enough parentheses so that at each given point of time, the addition is sticking to exactly two elements of the field. Similar remarks are true for multiplication. The fact that irrespective of how you put these parentheses, the result you get is always the same is a consequence of associativity. So by associativity, it doesn't matter how the elements are grouped. It does not matter how elements are grouped in addition. You can group them in any way you want. To actually prove that it doesn't matter how you insert the parenthesis and just by associativity you always get the same answer, you have to use a boring argument using mathematical induction that I will not be interested in. So we will just skip it. Okay. Similarly for multiplication, we also have the special case from the fact that we can define multiplication and addition of n elements. We have the special case, we can define a power n to be just a n times. We can define multiplication of a by itself n times. We can also define a power minus n whenever a is not 0 by a power n's inverse. Okay. Now, every single law of multiplication, addition that you have seen, including things like the law of exponents, a power m into a power n is the a power m plus n, all of these are consequence of these field axioms. You will be proving some of these in the exercises, like minus a into minus b, as you can guess, is just ab, and minus of minus a is just a, and minus of a minus b is just b minus a. Now, you just prove a few of these. It is not worthwhile to prove every single identity, but rather by solving these basic things, it should be clear to you that if somebody presents to you an algebraic identity and asks you to prove it, immediately you should be able to see the proof in your head. So just solve enough exercises till you are confident of this skill. There is no point in endlessly proving basic identities. It is a waste of time. So I will not ask you to prove a lot of them, just a few of them. Please, however, do solve all of these. Now, if you are a very, very ambitious person taking the course and you are very good in programming, a difficult and very, very, very time consuming program to write would be to write a program that takes as input an identity and provides a proof of that identity. If the identity is not really correct, it should also tell you that this is wrong identity. Now, this is an insanely challenging program. If only the most ambitious should attempt this. Okay, so this is the course on real analysis and you have just watched the module on field axioms. Thank you.